Today's lesson is on a circuit called the voltage divider circuit. And this circuit is foundational to a lot of applications in physical computing, and we've already encountered the voltage divider circuit, whether you realize it or not, several times this semester. The voltage divider circuit, simply stated, is a circuit where you have more than one electrical component hooked up in series so that they have to share the voltage that's supplied to them. They divide the voltage. And so you need at least two electrical components in series to build a voltage divider circuit. But it's more than that as well. There's a theory behind it, formulas that we can use to understand what's happening in the voltage divider circuit. So this lesson is going to be pen and paper based. I'm going to be showing you some example circuits and doing some algebra, applying Ohm's law to these circuits. And I'll show you a few special cases as well, or specific applications of voltage divider circuits. All right, so let's get started. Okay, so we're going to start with an example of a simple circuit with two resistors in series and connected up to a battery. So let me draw what that looks like. All right, so here it is, and I have a voltage source. And so if this is an Arduino, that's going to be 5 volts or 3 volts, 3.3 volts. And so then this voltage source here is supplying current to resistor 1 and resistor 2. And so the current's going to be flowing this way through the circuit. And so one thing we know is that since resistor 1 and resistor 2 are in series with one another, they both get the same current. They both experience the same electric current. So the current that flows through R1 is the same as the current that flows through R2. They're all in the same pipe for electrons, the same wire. Okay. So one of the principles that was presented in the written lesson for this week is that when you have an arrangement like this, the voltage that's used by resistor 1 plus the voltage used by resistor 2 equals the total voltage. That's the essence of the voltage divider circuit. So we can write that like this. The total voltage being supplied to the circuit equals the voltage drop across resistor 1 plus the voltage drop across resistor 2. Just like that. So that's called Kirchhoff's voltage law. The sum of the voltage drops across any closed loop in a circuit equals the total voltage supplied to that loop in the circuit. The fact that it's called Kirchhoff's voltage law isn't really that important. The principle here is important. Now, we can take this a step further, in that we know from Ohm's law that V equals I times R. So each of these V's can be written as an I times an R. So V1 can be written as the current through resistor 1 times R1. And V2 can be written as I R2. All right. We can also say that V, the total voltage supplied to this current, is equal to the current flowing through the circuit multiplied by the total resistance of the circuit. So we could say V equals I times R total. And if that equals I R1 plus I R2, you see algebraically you could divide everything by I, the I's cancel, and you get this algebraic relationship that when you have two or more resistors attached in series or connected in series in a circuit, the total or effective resistance of that arrangement is just the sum of the individual resistors. Like that. Okay, so that's a useful thing to know. So here's an application of the voltage divider circuit. This idea that voltage is shared between two components hooked up in series. Here's a circuit where there's a voltage, and that voltage, there's a battery, and that battery is supplying current to an LED. That's the schematic symbol for an LED right there. And it's a light emitting diode. So In order for this battery to supply current to the LED without burning out the LED, you need to give the LED what's referred to as a current limiting resistor. So that's what this R is right here. It's a resistor that's specifically picked with the correct resistance to limit the current and voltage being supplied to the LED. So we can use this principle of the voltage divider circuit to calculate what that resistance value should be. So we can engineer, we can design a circuit to make an LED work. So let's take a look at a real LED, a data sheet for a real LED, and then calculate what the resistance needs to be for a circuit where this LED is being powered by 5 volts from an Arduino Uno digital input output pin. All right. Okay, so here is a green LED, a basic green LED, and if I click on documents, there's a data sheet here. Let me bring it up. And the data sheet has a bunch of parameters for this LED. And so the things that you need to be able to do, one of the things you need to be able to do is to look at an LED data sheet and pull out the information that's essential for designing a circuit with a current limiting resistor that'll make this LED work. All right, so the things that are important here are the stuff that's contained in this table, absolute maximum ratings. Okay, here's that data sheet in another application where we can zoom in and I can mark it up. So the things that we want to pull out of the data sheet here, which tells us how to design a circuit to make this green LED work, is we need to know how much current it needs. So that's in the data sheet here labeled as forward current, and the units are milliamps, 20 milliamps. And we also need to know how much voltage is required. So there's a row down here that says, well, at this 20 milliamps, the minimum voltage this LED requires is 1.2 volts. The max is 2.2. And typical, there's no number given here, but what I'll do is I'll split the difference, 2 volts, halfway between 1.8 and 2.2. So to make this green LED work, what we want to do is we wanted to design a circuit so the LED's receiving a current of 20 milliamps and is getting a voltage of 2 volts. All right, so there's our design parameters. Let's go back to our drawing board and see how we can calculate what resistor we would need to make this work. Okay, so back here on our circuit diagram, I've written that the LED, the green LED needs 20 milliamps of current. Oops, I wrote that wrong. 20 milliamps is 0.020 amps, and the LED needs 2 volts. Okay, so let's think our way through this. If the total voltage being supplied to a circuit to power this green LED, and it's being supplied by a digital input-output pin on the Arduino, what's the total voltage that's being supplied to the circuit from a digital input-output pin on an Arduino Uno? If you said 5 volts, you're correct. So if the total voltage being supplied to this circuit is 5 volts from the Arduino digital input-output pin, and we want to design the circuit so the LED gets 2 volts, how much voltage should the resistor use? What should be the voltage drop across the resistor? Did you say 3 volts? I hope so. Kirchhoff's voltage law would say that the total voltage supplied to the circuit equals the voltage used by the resistor, VR, plus the voltage used by the LED, VLED. So if V total is 5, VLED is 2, VR is 3 volts. Okay. So here is all that's summarized. Okay. So the other parameter that we need to keep in mind here is the current flowing through the circuit needs to be limited to 20 milliamps. And so if we know the voltage being utilized by the resistor, 3 volts, and we know how much current needs to flow through the resistor, through the entire circuit, and that value is 20 milliamps, we can use Ohm's law to calculate how much resistance is needed to make that so. So the voltage drop across the resistor, VR, equals the current through the resistor, I, times R, the resistance of that resistor. And now we can solve for R. R equals VR divided by I, which would equal 3 volts divided by 0.020 amps, which equals 150 ohms. So to just recap here, we have an LED. It's a green LED. We look at its data sheet. It tells us that this LED requires 2 volts and a current of 20 milliamps. We know we're going to hook it up to an Arduino Uno digital input-output pin that supplies 5 volts. If we just hook the LED up to the digital input-output pin, and that's it, the LED would burn out quickly because it's getting too much voltage, too much energy. So what we do is we introduce a current limiting resistor, and then all that remains to be done is to calculate how much resistance that resistor needs in order to limit the voltage to the LED to 2 volts and the current in the circuit to 20 milliamps. And we use Ohm's law and Kirchhoff's voltage law to do that. So this is a voltage divider circuit. The voltage is divided between 2 components, and we can use Kirchhoff's voltage law, that the sum of the voltage drop across those 2 components equals the total voltage in the loop of that circuit loop. And we use Ohm's law to calculate what that resistance needs to be. And in this case, it's 150 ohms. Okay, so this is something I expect you to be able to do. If I give you a data sheet for an LED or the voltage requirements and current requirements for an LED, I expect you to be able to calculate how big a resistor you would need to put in series with that LED to limit the current flowing to that resistor so it works without burning out. All right. So let's consider another example. Here's a voltage divider circuit with a voltage supply, a pin on the Arduino perhaps, connected to 2 resistors in series, R1 and R2. But the second resistor right here is a variable resistor. That's what that line through it means. So its resistance depends on something. Maybe it could be a device called a rheostat where you turn the knob to change the resistance. But in this case, let's pretend that it is a photoresistor. It's a device that when light shines on it, it actually changes the resistance of the resistor. And so you can use this device and a circuit like this as a way to sense the intensity of light in a room. Well, how would that be done? Well, let's start with the voltage divider equation again and look at how the voltage utilized by R2 depends on its resistance and the other components in the circuit. All right, so Kirchhoff's voltage law says the total voltage supplied to the circuit equals the voltage used by R1 plus the voltage used by R2. And then if we expand that out using Ohm's law, V1 equals I R1 and V2 equals I R2. So we can then factor out I, and V equals I times R, the total resistance, R1 plus R2. Okay, so again we see that effectively the voltage utilized in this circuit is the current plus the total resistance of the 2 resistors in series. Okay, we also know that if we just look at V2, the voltage used by V2, it would equal current times R2. All right, and so what we can do is we can take this equation right here and solve it for I, and then plug that in for I down here. So if we solve that for I, we get I equals V divided by the total resistance. And then if we plug that in right there, we get a voltage divider equation, which says the voltage utilized by resistor 2 is going to equal the total voltage supplied to the circuit times R2 divided by R1 plus R2. Put that in parentheses to make it more clear. All right. So again, all I'm doing is just substituting this in for I up here. All right, so what we have is that the amount of voltage that is utilized by resistor 2, and again, here in this case, it's a photoresistor. It's a function of the total voltage being supplied to the circuit, which is a constant, 5 volts if it's an Arduino Uno digital input-output pin. It's a function of that and R1, but then also R2. So as the light intensity changes, R2 will change as well, the resistance of this photoresistor, and then that changes V2. So V2 is a function of R2. So, and R2 is a function of how bright the light is in the room where this photoresistor is. So if the light gets dimmer or darker, R2 changes, and that means V2 changes. So that means we can measure V2 using our microcontroller, and that tells us something about R2, which in turn tells us something about the light level in the room. So we can measure the intensity of light using a photoresistor by, or inferring the intensity of light by directly measuring the voltage being utilized by that resistor. Okay, so the way we would do that is, let me draw that. We would connect a wire to our circuit right here between the resistors to one of our analog pins on our Arduino Uno. And then we do an analog read and could infer from that the voltage at this point in our circuit, which is V2. It's how much voltage is going to be used by R2. And okay, so we could set that up, but let me pose a question to you. Here's a picture of an actual photoresistor. It's also called a photocell, and this one can be purchased from Adafruit.com. But when you look at the documentation, it says that when light impinges on the surface of the photocell here, its resistance drops. So as the light intensity increases, the resistance decreases. And in the dark, where there's very little light, the resistance is really big. So think about this. So in our equation down here, that's R2. If light is impinging on the resistor, R2 gets really small. What effect is that going to have on V2? If the sensor's in the dark, R2 gets really big. What effect is that going to have on V2? In other words, when the sensor, if you hooked up this sensor to your Arduino in a manner shown here, what would you measure if there's a lot of light? Would you measure a high V2? Would you get a big number on your analog read, or would you get a small number on your analog read? So think about that for a second. Pause the video, think about it, and then I'll give you the answer. Okay, you ready? So here's what happens. If you look at this equation algebraically, if R2 is really, really big, then R1 doesn't really matter. It doesn't matter as much. And this ratio right here, R2 over R1 plus R2, gets closer to 1. If R2 is really big, that ratio in the parentheses there gets closer to 1. So V2 is going to get bigger. It's going to get closer to V. In other words, when R2 is big, more of the voltage is used by R2. So the voltage would go up and your analog read value would go up. So if you hooked up this circuit to your Uno and did an analog read in the dark, you get a big value. Now if you did an analog read in the light, R would go down, R2 would get smaller, and if R2 gets smaller, R1 starts to matter more, and this ratio gets smaller. So V2 gets smaller. So if you put that resistor, that photoresistor in the light, R2 will drop, and that means V2 will get smaller. Less voltage will be utilized by the photocell. Did you figure that out? All right, so those are two examples of applications of voltage divider circuits for hooking up an analog sensor, in this case, the photocell sensor. In class, we used an analog sensor in the temperature sensor, and whether you realize it or not, we hooked that up in a way that set up a voltage divider circuit, and we measured the voltage that was being used by the temperature sensor. All right, we also looked at the example of a voltage divider circuit in the context of designing a circuit to make an LED work with the proper voltage and current so it doesn't burn out. So it lights up, but it doesn't burn out. Okay, so study these principles. You'll be tested on these principles. And until next time, I'll see you later.